Maybe you've seen YouTube videos about expanding your Arduino or your ESP32 to an unlimited number of GPIOs, unlimited number of output pins. All you got to do is hook up the shift register, the 74, was it 595, I think. We're going to take that to another level. We're not just going to talk about how many pins we can get. We're going to talk about how fast we can get them. And the reason is because I'm thinking about putting together my own DAC. R2R DACs are really popular. They're expensive. They're supposed to sound really good. They don't really sound all that complicated to me. I started researching DAC technologies, and it turns out the predecessor to the R2R DAC is actually the binary weighted DAC, which is simpler, but it's more complicated to get the resistor values right. So, thinking along those lines and maybe wanting to experiment with some of it, I thought to myself, well, I gotta have a way to get the digital number. It's gonna be coming at me over an I2S bus, right? So I need something that can receive that I2S signal and fan it out, right? We need to fan out that all those bits, the bits that represent the number, we need to fan it out so that we can then interpret those bits and transfer them over to an analog world. You know, high fidelity, hi-fi audio these days, it started out at, you know, CD quality is 44.1 kilohertz, 16 bits per channel. But kind of the minimum today is 24 bits per channel. That's the tricky part. That's the high definition. Studio quality, I think, is what's considered studio quality is going to be probably a 96 kilohertz sample rate. So what that means is that 96,000 times per second, both channels, 24 bits per channel, both channels need to have a number represented out onto individual bits so that they can be translated into the analog world. That's 48 bits. So I gotta have 48 output lines, outputs. And if you do the math, what you want to find out is how many, how often do you have to make, how often do you have to be able to make those, all 48 of those bits, how often do you have to be able to make them change? At 96 kilohertz, we're talking about 96,000 changes per second. So if you divide 1 by 96,000, you come up with a number that's around a little over 10 microseconds. So if you can get your all 48 of your bits written right in less than 10 microseconds, then you might be able to use an ESP32 as the brains for a DAC. High fidelity, high resolution DAC that's capable of at least 96K. You know, they go higher. You know, 192 and 300 and some, right? They go higher. 96 was what I kind of figured would be my minimum to even think about using this particular microprocessor if I was really wanted to do this. So that brings us to this video, and I've been experimenting with it. I've got a circuit set up here on the breadboard. I've got an ESP32 here. So this cable's going off to the laptop. The laptop's over here off camera. And the first sketch, Arduino sketch, We've got scope probes hooked in here. This one's on ground. The shift register has a data line and 4 control lines. The data line is the bit, the value of the bit that you're shifting on, right? And there's 8 bits. It has 8 bits worth of memory. The clock is the pin that you bring high when you want it to grab the data line. You bring it back low and you bring it back high again, it's going to grab the data line again. So that means you got to change the data line if you want whatever bit you're shifting it into to be high or low, right? So data line, clock, right? Data line high, clock it, and now you've got a high on bit 0. Clock it again, you got a high on bit 0 and bit 1. Bring it low, clock it again, now you've got a high on 2, 1, and a low on 0. There are 3 other control lines, 2 of which we don't care about. One of them is called output enable, and what that does is just makes the output pins hot. If it's not low, the output pins will float. They'll go open collector. We're gonna leave that at 0 all the time. The other one is a master reset. That's the other one. The other one we're not going to use. We're just going to leave it enabled all the time. The other one is key. It's called the latch. Now, as I said, if you can clock them on, but what you're doing is you're clocking it into an internal register, one that does not show up on the outputs of the shift register. They don't show up on the outputs of the shift register until you bring the latch high. Now it's really nice the way it's set up. And on the internet you'll also hear that you can gang these things up, right? There's another pin on there that is it's like the output of the shift register that you can then shift onto the input of another one. We're not taking it, well, we could have taken advantage of that, but because we need this blazing speed, we're not going to be able to take advantage of that. I've got a little sketch set up here, and what we're showing here, what we're doing in this sketch is we're just dealing with one of the shift registers on this board. This one down here on the end. It has a data line, the clock, and the latch hooked up to it. And then it's got, by these little wires up here, we are holding output enable low and holding master reset high. Now what the sketch does is I thought that I could maybe take advantage of the multi-core capabilities of the ESP32. And I set it up so that I had a task running on core 0 or 1, a different one than the loop. The loop is what will get the data and make it available to the task. All the task really does is read from an area in memory, a byte, and transfer the data in that byte out onto the pins of the shift register. Even though it says write out both channels, it's really only doing L0. L0 means left channel byte 0. They're all defined up here. Here's the 48 bits worth of data represented by 6 bytes. So if we look at what the task is doing, I'm scheduling the task with the Arduino, and it's running on its own core. So I've got this little print statement up here that tells you what core it's running on. And then it goes into this infinite for loop. Well, it turns out that you can't run an infinite for loop on a core without hitting a delay statement, because if you don't, the watchdog timer will time out and it'll throw an exception and it'll reset your CPU. To keep the watchdog timer from timing out, you have to call delay. And the minimum number you can pass to delay is a 1. Now that's milliseconds. And you heard me say a minute ago, we got to be able to get 48 bits worth of data transferred out to these shift registers every 10 microseconds. So that's going to be 100 times too slow. But this sketch was the one I started with to transfer the data out and to see if we could get our window, the amount of time needed to transfer the 8 bits of data for this one shift register out within, I mean, because at this point when I started, I didn't even know if we were even in the, you know, microsecond range. We need to get it out there in less than 10 microseconds. That means that we need to get it out there and then be able to do it again within 10 microseconds, which means you got to get it out there in less than that in order to be able to turn around and do it again. So what this does, if we look at the sketch here, it brings the latch low, and then it calls the do bit with a mask. And then up here, if you look at do bit, it does some binary if statements here, some binary logic statements to determine if that bit of the byte coming in is high based on the mask, and if it is, it will set the data pin to high, and if it's not, it'll set it to low, and then it'll clock it. And I've got this thing in here called tight delay because I was at one time thinking we were clocking it too fast. Turns out it wasn't. Pretty simple though, right? You do bit with a mask of 8, right? That's going to clock out a high or a low. You do it with a mask of 4. These are hex numbers, right? 0x here means hex. You send out all 8 bits, and then at the end of the routine, you bring latch back high. So latch goes low, you clock out your bits, those 8 clocks, then latch goes back high. Whatever data you clocked onto the shift register should then go out to the outputs. This sketch is running right now, and I'm going to hook up the scope. Let me bring the scope up here on the laptop. Channel 1 is the yellow probe. I'm going to put that on latch. Figure out which one latch is. Never can remember. I always get latch and clock backwards. I'm going to put that on latch, and then I'm going to put the channel 2 on clock. And let's see what we get. It says it's waiting. Why are you just waiting? Oh, there we go. Yep, that's what we expected. So we are on up here 1 microsecond per division. So if we count our divisions, why would this not slide? Slide over here. There's 1, 2, 3. A little more than 3, but not 4. So that's really promising. That means that in less than 4 microseconds, we can get all 8 bits out onto one shift register. But now the challenge comes, we've got to do 6 shift registers. This is just 1. We also have to be able to do this, and right now I think we put this in, take it out of single and put it in auto. Run it. And maybe we can get an idea of how, So the latches are at the top and the clocks are at the bottom. Every one of those spikes coming down, on the green side, there's going to be 8 clocks. So you can't even tell them, right, that the sample rate's not high enough. But right now, we're only getting, well, that's 1 microsecond, right? Or I'm sorry, 1 millisecond. That's exactly what our delay is, right? In our core, we delay 1 millisecond, and that's exactly how, you know, how far apart our yellow drops are. And that ain't going to cut it. So we're going to have to move off of this core idea or do it differently somehow. But it's promising enough to move on to the next experiment. So that we're going to hook up all 6 of them now. And when I say all 6, let me explain how I've got it wired up. I'm not using that ganging idea where one shift register shifts onto the next. I have enough pins on this. This ESP32 is totally committed to this application. So I have enough GPIOs to have 6 bits of data that I can put out onto the shift registers in parallel. So instead of just setting up the first shift register and clocking it, what I'm doing is I'm setting up all 6 of them, and I'm clocking all 6 of them and latching all 6 of them at the same time. And if you look at the circuit here, the orange jumpers that are running down the board, that is connecting latch and clock to each of the shift registers going down the board. And then coming from the ESP32, on these cables here, these are the data lines. So all the shift registers are receiving the same clocks, right, and the same latches, but different datas. I didn't show you the output. Let me go ahead and show that. What we got over here? We're looking at, I think we're latching on, we're looking at yellow, triggering on yellow. Oops, fell out. So you can see every other latch, the least significant bit, changes state, which is what you would want to see. You would see high, low, and the least significant bit. Then on the next most significant bit, the width of that will double, and that's what we're seeing here. The reason I've got this pattern going is because I'm doing a count. I didn't even explain that to begin with. The more significant the bits are down through here, the wider that pulse will get. It was somehow actually putting out the right signal without having power applied. But anyway, it looks much cleaner now. We're on the 3rd most significant bit of the chip, and we should probably be seeing 2 of these, and then double that would be this, and then double that would be out to about right here, which is probably about what we've got scrolling across the screen here. It's just not, it's triggering funny. If I go to the next one, it would be twice that, and I'll bring the times per division down, and we'll start to be able to see that. I go to the next one, it's going to be twice as long again. That's pretty much what you're looking for when you're verifying that it's doing a correct count. So yeah, we're looking good. Let's move on to the next sketch. In this sketch, we move the clock out of the do bit method, and we've got we've got it set up so that it writes out all of the data onto all of these ESP30, onto all of these shift registers. But it's, let's see, is it still in? write out both channels. Let me think here. So now, and now we're also just doing it in the loop, right? So we're writing out both channels from the loop, and we're setting up the data in the loop and all that. So this should be, this should not have that 1 millisecond delay between each write of the full data packet. And it will also make sure that it can do all, I mean, we know it can do it. The question is can it do it in less than like 10 microseconds? Because it has to be able to do it, all of them in less than 10 microseconds in order to be able to work as a 96 kilohertz DAC. So I'm going to write that down. I'm going to load that on the ESP32. Sketch is compiling right now. Okay, it's down there. Looking at the scope, green line right now is on a data pin. I'm going to put it up here on the clock. Okay. And remember, for every latch, every yellow, there's 8 clocks. So let's speed this up. So that's 20 microseconds. Let's go to 10 and pause it and see what the deal looks like. So that's about what we would expect. You've got the latch goes low. Then you got 8, let's see, 1, 2, 3, 4, 5, 6, 7, I think, 8 clocks. So that's working. Let me spread it out a little bit more. It's pretty good looking right there. Okay, so what do we have here? Because we have to take the time to set up 5 more data pins before we can fire the clock. Now we've stretched it out to, looks like 1, 2, 3, 4, 5, 6. Yeah, 6 divisions here on the scope. Let me count that again. Line that up. Yeah, 1, 2, 3, 4, 5, 6, and a little more than 6, really, more like 6.5. So we probably have to call it 7. And you know, and it's actually closer to 8 before we get back to the falling edge of the latch at 2 microseconds per division. So that's 14, and that's not fast enough. Not for 96. It would work for 48. It is screaming though. It looks really good as far as let's look at what the data pins look like. What the data pin looks like going in. Yeah, you see it varying. That's how it's as it counts up. It's probably easier to visualize it with this one on clock. Now the yellow channel is now on the clock pin. So it's kind of hard to see when one byte ends and the other one begins, but there should be a gap, right? Yeah. So there's a little bit of a gap right here, right? So right here we're clocking a 0. Right here we're clocking a 1, clocking a 1, clocking a 0, another 0, and clocking a 1, clocking a 1 here, and then clocking a 0. But it's not fast enough. And if we look at the sketch, it's 1 pin at a time. That means that there's a setup time that the Arduino enforces, I guess you'd say, for each pin. Well, we're talking nanoseconds at this point. So all is not lost, because the ESP32 has a register, 2 registers, 4 actually, but we're only going to use 2 of them. It's called write 1 to set and write 1 to clear. They're abbreviated as W1TS and W1TC. The nifty part about them is that they're 32-bit registers. Each bit represents a pin. So bit 0 is literally pin 0, right? Bit 1 is literally pin 1, GPIO pin 1. There's another bank. You've got 32 through 64 up there, the high ones. We're only going to use the low end. That means that you have to make sure, in order to be able to do this, you have to make sure that your pins that you want to write in parallel are all either on the low end or on the high end, and it's definitely easier to get them all on the low end. I did in fact have to rewire one of these. Had to move one. I think I was up on pin 33 or 35, something like that, and I had to move a wire down and get it down on something below, from 0 to 31 in order to do this. Let me load that sketch. This sketch is pretty simple to understand, right? It's using the same do bit with the mask, except that it's also passing in the pin to do the do bit on in order to pull off doing all this on it's multiple bytes of multiple channels. 3 bytes per channel, 3 bytes per audio channel. So we've got another array that sets up the pins, and as we're working through the mask, it works the mask on the pin that's sent down there. So we've got these 4 next loops that go through each byte, and it changes the data in the pin index and then passes the mask. I know it's you could hit pause. Everything's on the screen right here. You could hit pause and just try to get your head around it for a minute, but it's basically it's just getting them all, getting the data set up on all of them, and then clocking it. So then we have a clock here, and then changing the mask and doing the same thing again. And then at the bottom, of course, at the top would bring the latch low, and at the bottom, of course, would bring the latch back high. But this is not fast enough. So let's go see if we have another sketch out here. I hope we do, because I saved it out here. In this sketch, we take advantage of the reg write command. Now here in do bits, you'll see that we are we moved the clock back up into do bits. So we're going to clock out, or we're going to write out all 6 data bits at one time and clock them. So down here and write both channels, you can see we're doing something doing the same thing. We're passing in the mask. And up here in do bits, we're going to each byte from left to right, incrementing the index. And then what we're doing here is the really nifty part, right? We're checking the data at the index against the mask, and if it's low, then we are shifting a 1 onto a low bits variable. No, so we're not shifting onto low bits, we're ORing with low bits, whatever we had before in low bits. Low bits always starts out empty. Okay, so in this array at index 0, if the number there is a 5, then we will shift a 1 left 5 times. And OR that with low bits, right? So that's saying that it's actually OR is basically an add. So you're saying that low bits equals low bits plus the pin, the number of the pin, the bit that the pin represents, and then you do that for if it's low. If it's not low, do it on the high bit side. I'm sorry, I probably didn't do a very good job of explaining that. It's all right here though. You can hit pause and should be pretty easy to figure out. Let's go ahead and run this sketch. I should have got that going ahead of time. Let's get on the latch and the clock here. Well, that's happening. I don't want to stay in there anymore. I'll probably have problems with this breadboard from shoving these probes down in the down in the holes and wearing them out. Okay. All right, I think it's running. Let's capture a waveform. We're at 2 microseconds. And hit pause. So it looks quicker. Looks like I've got clock and latch backwards from what we've been looking at earlier, but I've got the latch. It looks like it's on the channel 2, the green channel. So it comes down, and then we get our 8 clocks. And the amount of time it takes for between latches is really what we're concerned about. It needs to be less than 10 microseconds. So let's count them out. We've got 1, 2, 3, 4. Definitely less than 4, but in order to get, this would be 5. So 1, 2, 3, less than 4 to set up our data and get it latched. So that means we can do it, right? That means it's less than 10. It's actually a little more than 10. I don't remember the exact math, but and then can we get set? Can we? All we have to do is basically get to the point where we can bring our latch low again within 10 microseconds. I'm on 2 microseconds per division up here. So 2, 4, 6, 8. This right here would be 10, and we're well into it. We're already well into the next frame by the time that rolls around. And I've actually got a little more time than that. So this could actually be spaced out around over here where my mouse is before it really needs to go low again. So we can do 96. But hey, I mean, if it wasn't for this right to set, right one to set and right one to clear, we wouldn't be able to. I think I'm going to go ahead and continue the build. So the way I'm looking at this is you got your ESP32. We're going to break this up basically into 3 blocks. You've got the input side of the ESP32. This is where the I squared S signal will get pumped in. You've got this is the digital output side of the ESP32. That's what we're working on right now. We're actually pretty much completed it. The data will be picked up by it, right, and put over here onto discrete bits in a digital form out on to be transferred over to the analog block. This is now we have the analog block. where we have to build D to A converters. And through the wizardry of what we call voltage summing amplifiers or voltage adders, it's basically just a kind of a network of resistors in front of an op amp. The voltages that are on the other side of those resistors, if you have all these resistors, let's say you have all these resistors, right? And over here, you have an op amp. These are tied together here and they're just feeding the op amp. Let's say on this side over here, if you have 1 volt here and 2 volts here and 4 volts here, this adder voltage summing amplifier will produce on the output over here 7 volts. It'll add them up. With that capability, we're going to be able to do our D to A conversion. So that's a little bit in the future, a little preview, hopefully, because I do think I'm going to continue this build and see if I can make this thing sound really good. I think I'm going to have to order something in order to get an I2S signal to the ESP32. And then over here on the analog side, there are some serious challenges because the voltages that we will need to produce for the least significant bits of these channels are so small we probably won't be able to measure them. We'll just have to believe they're there, and we'll have to believe we can hear them. So, all right, well, that's all for now. I appreciate you checking in with me, and I hope you find this kind of stuff interesting. If nothing else, I hope you learned about how you can write out your GPIOs on your ESP32s much faster than and in parallel. You know, you can write many at the same time and not have to like go bit to bit to bit to bit in order to bit fiddle whatever it is you need to bit fiddle out there in your project. So thank you, and we'll catch you later. And you know, to be able to do 96. Now I don't have any experience. Ooh, the camera kicked off and scared me to death.